History of thermodynamics. Thermodynamics is the science of energy transfer and its effect on the physical properties of substances. It is based upon observations of common experience which have been formulated into laws of thermodynamics. Its applications are found in all fields of energy technology, in internal combustion engines, steam and nuclear power plants, refrigeration and air conditioning, gas dynamics and jet propulsion, compressors, energy conversion devices like solar cells, etc. Industrial Revolution ushered man into the modern world of machinery and manufacture. Some brilliant individuals like Thomas Savery, Newcomen, and James Watt are associated with the invention of steam engine. Watt brought considerable improvement in the performance of steam engine. George Stephenson introduced steam engine in rail transport. Robert Fulton used it in steamboats. Steam engine gave stimulus to the birth of thermodynamics, and therefore thermodynamics is considered as daughter of steam engine. After the run for finding energy out of nothing, that is perpetual motion machine of first kind PMM1, inventors started developing concept of law of conservation of energy. The first recognition of this principle was made by Leibniz in 1693 when he referred the sum of kinetic energy and potential energy in a gravitational force field. Until the middle of 19th century, heat was considered as a fluid. Interesting, right? Colorless, weightless, odorless heat flowing from body of higher caloric to a body of lower caloric. This concept is known as caloric theory of heat, first proposed by Antoine Lavoisier, the father of modern chemistry. At this point, the words like saturated liquid, saturated vapor, etc. got originated. This theory got proved to be false and heat was confirmed as a form of energy in the middle of 19th century, leading to the formulation of first law of thermodynamics. Benjamin Thomson, James Briscoe Joule, and Julius Robert Mayer are notable personalities. Benjamin Thomson, also named as Count Rumford, while boring Cannon Hall, noticed that there was a continuous heat release due to friction. From the established principle of conservation of mass during that time, a true fluid can neither be created nor be destroyed. So how heat can be a fluid? Since it is continuously produced. But Rutherford conceived that heat was a kind of motion and the vibrating motion of particles in the object created the heat. In the early 40s of the 19th century, Joule and Julius R. Mayer almost simultaneously set forth the idea that heat transfer and mechanical work were simply different forms of the same quantity, that is, energy in transit. Mayer's equation was formulated as the difference between specific heat at constant pressure and specific heat at constant volume gives the real gas constant. While ideal gas equation used commonly nowadays was derived by Clapeyron long after finding Mayer's equation. Joule was the ultimate experimentalist. From where Rumford left, Joule started. He found that The flow of current in a resistance is accompanied by the development of heat proportional to resistance. So he concluded into a formula W is equal to JQ. This equation was his conclusion, and where J is mechanical equivalent of heat. As his paper went rejected and received incredulity in 1843 and 1844 respectively, he started experiments which proved impossible to refute. He conducted an experiment in a pool, that is, heating a pool of water by an array of paddle wheels driven by falling weights. He also suggested to the society that water at the bottom of Niagara waterfalls should be warmer than at the top by 2 degrees Fahrenheit. From the thermal expansion of gases, Joule deduced that there should be a zero of temperature 480 degrees Fahrenheit below the freezing point of ice, which is now considered as absolute zero condition. William Thomson, who later became Lord Kelvin, got interested in Joule's results. And the first person to invent a theory simultaneously involving the ideas of conservation and conversion of energy was Nicolas Leonard Sadi Carnot. Carnot was a French military officer. Carnot was convinced that France's inadequate utilization of steam power plant had made military inferior. The steam power which is used in England those days were improving their military and industrial infrastructures. Carnot was trained with hydraulics, pumps and water wheels at the École Polytechnique. Till Carnot's time, thermodynamics was developed on empirical chemistry. He approached an engineering problem, the efficiency of heat engine. The temperature differences which is necessary condition for mechanical work production by heat engine. His first conclusion of working of water wheel idea is extended to a steam engine by replacing water by a heat fluid caloric later, which paved way to Kelvin Planck's statement. The maximum efficiency of a water wheel was in part to the concept of maximum efficiency of heat engine. It is possible if there is no frictional or other losses. Carnot died at an earlier age of 36 years due to cholera. Rudolf Clausius and William Thomson worked out clear formulation of the conservation of energy principles. Carnot's first conclusion was then called the second law of thermodynamics by Clausius. Thomson used Carnot's second conclusion to develop concept of absolute temperature scale, and the mathematician Clapeyron constructed thermodynamic cycle by deducing that it must be composed of two reversible isothermal processes and two reversible adiabatic processes, and later known as Carnot's cycle. William Thomson then used the terms thermodynamics and mechanical energy for the first time. Clausius recognized entropy and assigned the symbol S. Max Carl Ludwig Planck demonstrated the connection of second law and the concept of reversibility. The impossibility of a cyclic device which produces positive work and exchange heat with a single reservoir matched with the similar concept of Kelvin's statement. Poinsett extended the work of Planck and prescribed a complete structure of classical thermodynamics. Thank you.